bad one. But let's get to it. So here's where we got to, right? We said there is evidence that supports the Big Bang Theory. There are different theories of the universe, but not many of them have as much evidence to support the theory. So the Big Bang Theory is the most widely accepted, okay? That our universe is currently expanding, and it started at a singularity 13.8 billion years ago. Now, interestingly, has everyone got a booklet? If you were absent. Everyone got a booklet? Okay. Interestingly, when this model was first proposed, Hubble back in the 1920s and 30s, it was a very conservative time. And the Catholics did not quite like this theory because it didn't really agree with their doctrine. And one of the high-up priests or archbishops of the Catholic Church initially mocked the idea and used the term, or in the phrase, so you're suggesting that the universe just somehow started by some Big Bang. He used it initially to mock the theory. But the scientists went, hey, Big Bang Theory, that sounds good. And it stuck. And so what he was trying to attempt to mock the idea, ended up naming the whole thing. Okay, so that's where the Big Bang Theory comes from. Have you got a booklet, Robert Lee? It's actually a pretty good throw. All right, now, the last evidence. So if you want to go for evidence that supports, you pick Hubble's constant cosmic background radiation. Those are the two big ones. But then the 3-to-1 ratio, that's another good one, because in the early days, mostly hydrogen and helium dominated. A little bit of lithium and a little bit of boron, helium-4, helium-3, a little bit of the lighter elements, but mostly hydrogen, helium. And we said the 3-to-1 ratio. The next is if you can look really, really far away. Excuse me, Hamish. I'm trying to talk. If you look really, really far away, are we going to have problems? No. You keep talking. We're having problems. I don't want problems. No problems. If you look really, really far away, you look really, really far back in time. And so the furthest we can see is about 13 billion years away. You're looking at galaxies when they were young. And young galaxies behave differently to old galaxies. So you look close, oh, there's a galaxy, it's old. You look far away, oh, look, a little baby galaxy. It's 13 billion light years away. We're seeing it as it was as a young child. It's currently a geriatric galaxy, but the information we're getting is a young child. There's a time delay between Mahoney and me, very, very small, nanoseconds. If Mahoney was 13 light years away, I would see him as a little 4-year-old. And I'd be getting the information of a 4-year-old Mahoney rather than an 18-year-old Mahoney. That's whatever, 17, 18. So, you've also got this. Now, this couldn't happen until this. This was freaking awesome. Now, the Hubble telescope, it was launched back in the late 1980s. And it had a massive mirror it's about 2.5 meters wide, a big reflecting telescope with a massive spherical mirror that could see the furthest. It was the biggest telescope that was made in a satellite. Obviously, you've got to get above the atmosphere to get rid of all of the disturbances of the atmosphere. What word do we call it? Distortion, thank you. Aberrations, probably even better. So up it went. But there was a problem. Its mirror behaved differently under one atmosphere where it was made to 0 atmospheres, and so it was myopic. It was blurry. All of the images that came back was like Mr. Murray without his contacts in. They had to go up on a Mercy mission. They spent hundreds of millions of dollars. So they went up and they corrected the mirror. And the first mission it had. And the Hubble is still up there taking measurements. You can, if you have enough money, you can book time for the Hubble and say, I want it to look there for this long with this frequencies of wavelengths and blah, blah, blah. The first thing it did is it looked at a very dark point in the sky. It looks near Ursa Minor, which is a bear constellation. And if you see on your image, there's a very, very tiny L-shaped Tetris piece. It's 2.6 arc minutes in height. So again, there is the moon for reference, and it's probably better if you look at it on the picture, you might be able to see that little yellow square. So for reference, your thumb is a degree, your moon is half a degree, it's looking at 1/30th of a degree of the sky. So the example is, you take out your Sharpie pen, you put a dot of ink on your thumbnail, and you hold it up at arm's length, and that's where the Hubble telescope was looking at. That's where it set its camera, okay? Now, it's kept the aperture open for 10 days. Meanwhile, it's in orbit around the Earth, okay? Now, if I'm doing that, Campbell is wobbling due to parallax, okay? I'm the Hubble telescope going around the Earth. Campbell is wobbling because he's not very far away. But if Campbell was, say, I don't know, at Cottesloe Beach, and I'm here doing that, parallax is not going to be an issue. So it just had to focus its camera at a point in the sky, obviously conveniently if it's perpendicular to the plane of orbit, but you know, don't have to worry about that. It kept its aperture open for 10 days, and all of the photons that were coming from that area of sky, 2.6 arc minutes of angular size, entered its telescope, okay? Now, it sent the image back, and there's a famous video of all these nerdy early 1990s astrophysicists gathered around this tiny little 15-inch cathode ray monitor, you know, your old school computer TVs, very, very poor resolution, and it's slowly coming through, and they open it up, and they're all cheering, all these nerdy people popping bottles of champagne. Because here is the image that came back. No, that's the image. Now, in this image, there are 3 objects in the foreground. They are stars in our Milky Way. They're the ones that glimmer. So there's the blue one down there, there's an orange one there, and then there's another orange one just up there. So there are stars in our galaxy. Everything else, there are 3,000 flecks in this picture. They are all galaxies themselves, each containing on average 100 billion stars. So every single fleck that you can look at is a spiral galaxy. Well, many of them are spiral galaxies. And they counted about 3. If we're talking about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, they're all galaxies, 100 billion stars. And so if you zoom out, 3,000 items, approximately 100 billion in each. I'm bad at maths, but that's about 30 trillion stars, I think. It's a big number, okay? Just in that little region. Recently, they took another Hubble image. So this is called the Hubble Deep Field image. They took another ultra deep field image because a couple of decades later, when maybe the telescope wasn't being used, they said, well, maybe we got lucky that maybe there's just a big concentration of galaxies that just happen to be behind Ursa Minor. So let's look in the other hemisphere of the sky. Let's look in the opposite direction. So they did the same thing. And they got exactly the same kind of image. There is just a shit ton of galaxies out there, and we are not very special. Sorry if your teachers have told you. Oh, I'm cool. We are all very special, as far as we know. Quick, dig up, Mr. Ray. There is something called the Drake equation. So, this is a fun, if you've heard of the Drake equation, what Professor Drake did is they go, okay, we know, you can do some very quick maths with this image. From what we see in that tiny image, you look at what fraction of the sky it occupies. You divide by that fraction and you get a large amount of galaxies with a large amount of stars. So that's your starting number. And then what Drake did is he goes, I wonder if there's any extraterrestrial life out there. So what you do is he multiplied the number of stars by diminishing probability. So the first one is that your star has to be of a nice size, of a long enough age, Then that's the first one. And so you maybe 80% of all the stars are good stars. Maybe 60% are good stars. The rest are nasty. Okay. The next one is you've got to have lumps of rock that are orbiting this star. And so you look around and you take some empirical data and, okay, multiply your number by another diminishing probability. Then you go, okay, some of these rocks you've got to be a certain distance away. Because if you're too far away, it's too cold, too close, too hot. Got to be in the Goldilocks zone, just right distance. Then it's got to have liquid water. Okay, another diminishing probability. Then it's got to be plate tectonics with venting of gases for greenhouse. It's got to have an atmosphere. Keep multiplying by smaller and smaller diminishing probabilities. It's got to be there long enough that a life could form. And then that life has to form a civilization. And then that civilization has to become intelligent. Again, diminishing. This guy's just sort of making up all of it. Well, not. He's figuring out what these probabilities could be. You take that first number, and even though you keep dividing by these diminishing probabilities, he still came up with an idea of millions of possible civilizations out there. But you'll never be able to prove it. There's one last image that I'd like to show you, and I'm not sure if I'm going to find it. I'm going to find radio waves travelled since creation. There's a really good image, and I'm not sure if I'm going to find it. Here we go. Yes. No. Yes. No. Yes. Yes. View, Mr. Murray. View. Yes. Okay. This is an artist's rendition of our galaxy. So you're looking at a spiral galaxy, head on, broad on. Remember, it's about 100,000 light years apart, and we are about there. There's a little blue speck, okay? That little blue speck is a circle of radius 200 light years. So that little blue dot there, which is zoomed in from that arm of the spiral galaxy, that's a dot of radius 200 light years. So it's 400 light years in diameter. That's how far the earliest broadcast of radio has travelled. So, bless you, if you are an alien civilization that happens to be there, they're not seeing us. They're seeing, I think the first person was Marconi Italiano, probably recited the alphabet. Alpha, beta, gamma, delta, I don't know. Elmo Marconi, I can't remember. The first bloke that made it. They're going to see us from the early 1800s. And the aliens are going to go, that's the issue. Like, you're never going to be able to see a civilization as they are. You're going to see it as how long it took the information to get there. Okay? So that's a lovely little... If we want to try and communicate, we are limited by the speed of light. So we're kind of alone. Or at least we're only able to look within... And again, we find a civilization that's 100 light years away. It's going to take 200 light years to get a response. It's a pretty bad ping. You can't play your Apex Fortnights. Okay? So just put it into perspective. At the moment, speed of light is as fast as we can communicate. Okay, I'm way off track. Let's get back to timeline. So, over the page, please, please read that timeline of the early universe in your own time. But I just want to go through a couple of things. So, basically, Cameron, please. Tom and Hamish, please. There was one question in the 2017 WACE exam that spoke about the timeline of the evolution of the four fundamental forces. So we're going to get that down because Mr. Murray didn't actually teach that in the 2017 year. That is my albatross that I have to bear. That there was 1 mark out of 180 that I hadn't taught. But one of the students did say that it was in that chapter in that book over there, and he read it and he saw it and it was listed in order. So if you read the textbook, then you're okay. You don't have to just listen solely to Mr. Murray. The model of the expanding universe is very similar to the ideal gas laws, that as you expand your volume, temperature and pressure goes down. So first off, you can split your universe into different times, different epochs, Brendan, where the temperature and pressure enable certain things to occur. So in different epochs, different things are happening. And I want us to just look at a few of them. The first thing I want you to be aware of is, obviously, you'll notice that our epochs are basically looking at different energies or temperatures. And you might see that the temperatures are decreasing as the age of the universe goes on. Okay? So at the start, basically anything before 10 to the negative 43, we don't have a heck of a clue what the hell was happening back then. So 0.42 zeros and a 1. Anything before that, it's called the Planck epoch, where they go, I don't know what's happening back then. Can't really tell you. Okay? Now, down here, you've got energies that we can reproduce. We can accelerate particles to 100 MeV. We can accelerate particles to a trillion. So down at about the quark epoch, we can get particles up to that energy. And that's what they will often say. It sounds very romantic when they say, at CERN, we are replicating the time of the universe 1/1,000,000th of a second after the Big Bang. Well, what they're really saying is that we can get you to sort of the quark epoch, a picosecond to a microsecond, because we can give particles 0.1 GeV. Okay? But at the moment, we're capped out at about a 12 tera EV. So even if we went up to a tera EV, we're not there yet. We can't get back to our electroweak epoch. But you often hear it being said in documentaries and news articles that they're replicating the first millionths of a second of the Big Bang. But really, there was a lot of stuff going on before the first billionth of a second. There are, in fact, 3 other epochs. Now, the question in the 2017 exam was to identify when the 4 forces evolved. So could you just identify the strong force becomes distinct at around here. And at that time, the 3 others, gravity and weak and electromagnetism, were all combined in what was called the electroweak interaction. Oh, sorry, I missed one. Yes, gravity is separated. My bad. Phew. Thanks for that spot, J-Bon. So gravity separated first. The 3 other forces were all sort of combined into the electronuclear, I should say. And then the strong force became distinct, and then you had electromagnetism and the weak combined into the electroweak. And then finally, if we go further down, let me just get rid of that. Where do they separate? The 3 forces are separated. When does electromagnetism split?
Yeah, the electroweak breaks into weak and electromagnetic.
Thank you. So guys, I will admit my knowledge on the evolution and the epochs of the universe is a little bit low. At most, the only question that has been asked in the past 3 years was that 1-mark multi-choice, circle the correct order of evolutions. And so it is gravity, then strong, and then lastly was electromag and weak. Okay? Now, couple of important ones that I'd like to just touch upon. In the first second to 1,000 seconds is our Big Bang nucleosynthesis. This is where, actually, take a step back. Just before that, quarks can make hadrons here. So in the quark epoch, they can make hadrons. Think of the analogy of steam is too high a temperature to condense into liquid water. So you've got basically individual molecules of water all bouncing around because their temperature and energies are too high. You have to expand that volume, let your steam cool down to a condensing point where they can then clip together and make droplets. Okay, that's the kind of the analogy of when your quarks can make hadrons, and then you've got protons and neutrons can be formed. So down here, this is where we said in yesterday's lesson that in the early stages of the universe was acting like the core of a star, that you had enough temperature and pressure to fuse light elements together. Hydrogen into helium and deuterium, helium-3 and 4, small amounts into lithium-7. But that was it. Because after 10,000 seconds, the universe kept expanding, pressure and temperature dropped, and the whole fusion event stopped. And that's what we said, well, if it stopped there, what should we see? And that's what the scientists said. We should see about a 3-to-1 ratio of hydrogen to helium with a few trace elements of lithium and helium-4 and helium-3. Okay? And that was it. The crazy thing is, and I'm not 100% on how to explain this, light was still not able to travel through the universe. So there was no evidence yet that this can occur. Go over the page. When the universe first becomes transparent, this is basically as early back as we can see. Okay? So this is the whole 380,000 years later, the expansion continues, and now light is able to travel. And we are able to detect that light. So the earliest things we can see are from 380,000 years after the Big Bang. Okay? But we can replicate events with high energy particle colliders. Okay? So, just highlight here, this is where the photons of our cosmic microwave background radiation were visible. Photons of our CMBR originate. Okay? And obviously, before then, all you had was a 3-to-1 ratio of hydrogen to helium and a little bit of lithium. And so that's what they were looking for. Then, the most remote galaxies, where do the formation of our first stars happen here? The Dark Ages is because not a whole lot happened. Stars hadn't formed yet, so there was no light. No stars had ignited. The analogy is, it took about 380,000 years for gravity to start coalescing. Here's the analogy. You have a big box of Lego bricks, and you just throw them into the classroom, and they're just floating around in the universe, which is your classroom. It's going to take quite a long time for those Lego bricks to start to clump together. Gravity is acting to pull them in to form your first proto-stars. So whereas my formation of first stars took a while, and during that time, no light, because fusion hadn't occurred yet. Remember, when fusion occurs, you release energy, and that's when your stars start to heat up and ignite, or start the fusion process. So, the only source of photons was hydrogen jiggling radio waves. So that's why it's called the Dark Ages, because there was no visible light. There was just hydrogen jiggling. And we might have seen, or in fact, no, you wouldn't have seen visible hydrogen. It was just emitting radio waves. Interestingly, that is the frequency that is being sent off with the, I'm having a blank. The two satellite, the Voyager missions. Has anyone heard about the Voyager missions? They sent out 2 satellites. One, they've now since left our solar system, just recently. They were launched back in like the 1970s and 80s. And one went that way and then looped around Jupiter and then travelled off into the emptiness of space. And the other one went around Saturn and then towards Pluto to take a few snapshots of Uranus and Pluto. They've since left our solar system. because they're now outside the orbit of Pluto. There's a great story behind what if this satellite, it was powered by a radioisotope battery with a half-life of several decades, right? Because once it gets far enough from the sun, solar panels don't work, so it needed to use nuclear radioactive alpha emitters to charge a battery. They said, what if this thing's picked up? Well, first off, it's got to be made of a substance that's so stable that it wouldn't just decay and crumble. An alien civilization might collect this thing 1 billion years later if it slowly aims towards another galaxy. They put a big gold disc on the side, and it had to be an isotope of gold that was stable, and they etched into it the images of man. In fact, I think it was man, Adam and Eve, a famous painting. Or was it that one? Was it that one? The something man?
The anatomy.
Leonardo da Vinci's Vitruvian Man. They had sounds on a disc. They had like it etched onto like a vinyl record in gold. Sounds of different tribes, babies crying, whales, sounds of earth. But also they put into it, they put a map of where we are in the relative galaxy. They put the hydrogen emission lines of radio waves. Because have a think. Shh. If an alien species is on the other side of the universe, they're going to be making the same tables. They're going to be figuring out the same epoch would have occurred where only hydrogen radio emissions were in this dark ages. So let's tell them that we know about the age of the universe. And then they had a couple of images of triangles and Pythagoras. There's an incredible story behind this gold plate that was commissioned to be put on the side of this probe, just in case. Because it's gone. It's left our solar system. Anyway, present time. So, the earliest things we can see. The earliest things we can see, please, the cosmic microwave background, as soon as the universe became transparent, boom, that was the first things that we could detect. It wasn't for another 150 million years until stars were first formed, and then galaxies. And so the most distant galaxy we can see, 10 billion years ago. I will now leave you with Derek from Veritasium. Which is why I have been in potato mode this whole time. Here we go.
There was a time when the universe was expanding so rapidly that parts of it were moving apart from each other faster than the speed of light. That time is right now. A lot of people make a big deal out of the fact that during inflation, right after our universe burst into existence, the whole universe was expanding faster than light. Now, while that is true, it kind of implies that the universe doesn't normally do that, and it does. I mean, if you pick 2 points far enough apart in our universe, you can always find ones that are moving apart from each other faster than light. That is simply due to all of the expanding space in between. So, our universe is now and has always been expanding faster than the speed of light. But doesn't this violate Einstein's special theory of relativity that says nothing should be able to move faster than light? Actually, no. Relativity says nothing can move through space faster than light, but that doesn't stop space itself from expanding however it likes. Now, it was Hubble in the late 1920s who made the observations of the night sky, which led us to see that our universe is expanding. The further out in space he looked, the faster the objects were moving away from us. So imagine a point so far out there that the average recession velocity is the speed of light. I mean, if you think about it, it's going to be the same distance in every direction. So that would form a sphere, which we call the Hubble sphere. Everything beyond that sphere is moving away from us faster than the speed of light. So common sense would say we would never be able to see the light from those objects because of how fast they're moving away from us. But in fact, this is not true. We can see those objects. To understand how this could work, picture a galaxy beyond our Hubble sphere. It's receding faster than light. It's in a superluminal region of space from our perspective. So any light that emits in our direction will actually be moving away from us as time goes on. Well, that doesn't sound very promising. But due to the accelerating expansion of space, our Hubble sphere is actually getting bigger. And if it gets bigger faster than that light can get away, then at some point that light is going to travel from a superluminal region of space into a subluminal region of space, and so it can start making progress towards us. So we can detect it, so we can see that distant galaxy, which is of course now even further beyond our Hubble sphere. But we can see its light. We can detect that it's there. This is remarkable. In fact, all of the photons we now receive from the first 5 billion years of the universe, they were all emitted in regions of space that were traveling at the time faster than the speed of light relative to us. The objects that emitted them were, are, and always have been moving away from us faster than the speed of light. But their light has entered our Hubble sphere and had enough time to reach us, and so we can see them. So the observable universe is larger than our Hubble sphere. It's actually limited by what's called the particle horizon. That is based on the amount of time light has had to travel towards us since the beginning of time. That is 13.8 billion years ago, as far as we can tell. Now, because the universe has been expanding and that expansion has been accelerating, things are much further out than 13.8 billion light years away. I mean, the observable universe has a radius of over 46 billion light years. The diameter is about 93 billion light years. That is a huge volume of things that we can see. And 13.8 billion years ago, everything in that volume and everything beyond it that we can't see would have been compressed into a tiny, infinitesimally small point that we call the singularity. Actually, no. I mean, that would be true if the universe is finite, but if the universe is infinite, and it kind of looks like it is, then it was always infinite. So the Big Bang would have happened literally everywhere. But if the universe has always been infinite, then what is it expanding into? Well, it doesn't have to expand into anything. I mean, it can expand into itself. That's the thing about infinity. You never run out of it. This episode of Veritasium was supported by Audible.com, a leading provider of audiobooks with over 150,000 titles in all areas of literature, including fiction, non-fiction, and periodicals. This week, I wanted to...
Okay, now, last thing from me. Unfortunately, this image should have been dropped down a little bit. There is a graph that shows you the relative times and temperatures and energies that the four forces separated. Just here, that image should have been a bit lower. We speak about this, I teach this to my year 11s when we do fusion, that fusion is occurring in our star, but our star is too light, and all it's ever going to make is hydrogen, helium, lithium, and beryllium, I think. Over the page, stars heavier than ours can produce carbon, nitrogen, and oxygen. Anything heavier than that has to be produced by a dying star that goes supernova. So it's going to be a really, really heavy star. Okay? Now, this is where my knowledge of the different types of stars and the different timelines of stars is a little bit lacking, but Brian Cox says it quite romantically that he goes, the atoms in your right hand are made from dying stars, from stardust that got shot into the universe from a dying star. And they're going to be from different stars than the ones that died in your left hand. So we are all made of heavier elements, elements heavier than oxygen. All right, so we've got lots of these atoms in us. So we are made from dying stars. So that's a very, very romantic way of looking at it, but we can chop you down a level by going to the Hubble Deep Field and going, well, we're just a little fleck in the universe. Then there's some questions from the review. I just want to show you an unfortunate year for you to be a Year 12 student. No, well, we don't know that yet. I'll make the comment at about 12 o'clock on Friday. No, I don't know when your exam is. The 27th. Friday the 27th at about 12 o'clock, I will tell you. This is this question here, okay? This is what they were confronted with. And it was talking about the evolution of the four forces. So gravity first, then strong, weak, separated last. But then there was also this really nasty question about the graviton. And it can be answered a number of different ways. And so if we refer to the marking key, it goes, well, zero mass, and the range of force is infinite, and it weakens with the inverse force, therefore it must have zero mass. Could also explain that the force of the infinite particle must be travelling at the speed of light. Gravity travels at the speed of light, so its charge-carrying particle must also then have a mass of zero, so it's not detectable. So you're suggesting a characteristic and give a reason why it's undiscovered. Zero charge. Well, it's not mediating charge, and so charged particles have already been detected. So that's why it hasn't been detected, because it doesn't have a charge. And then you could go off the syllabus and talk about spin 2. Odd spin forces result in repulsive forces. Gravity is not a repulsive interaction, so it's not a non-odd spin, i.e. 2. Nasty question, okay? This is my opinion and does not reflect that of the Standards Curriculum Authority or that of the school, but this was a very, very nasty exam. There were lots of questions in here that were nasty, and it was nasty. Okay? But they've learned from their mistakes, and they're not going to put nasty questions in this year.
Was 2017 the worst exam?
Yeah, apparently it was just
In distant memory. So basically, the syllabus changed. Look, he's asking a question, and I'm trying to answer, and he's just like giving up. Do you want me to answer or not?
Yes, please.
The syllabus changed in 2016, and in 2016 they added more of the standard model, they added more of cosmology, they added the Lorentz factor. Prior to that, all you needed to say was moving clocks tick slower, moving lengths appear shorter. That was it. You didn't have to calculate any times or distances or even energies. They added that all. They added the standard model poster. So quarks, the whole standard model was basically introduced, and you were asked to then consider conservation of baryon and lepton. So the 2016 exam was sort of thought of as they're just sort of dipping their toes into the new syllabus. And then they went, right, 2016 is gone, let's make a more heavy exam. Again, this is my opinion. And they asked some really, really nasty questions. Okay. So, again, you will be in preparation for the WACE. Go back and look at the 2018. Go back and look at the 2017. Obviously, there are still a good 140 marks of good, solid questions that you can still use as preparation. But just remember, there are a few nasty questions that were, imagine you were sitting in an exam and you had to do that one. It was just not nice. Yes?
What topic are the most nasty questions from?
I'd probably say relativity. But I go beyond the syllabus in relativity. We do some tricky calcs, we do the tricky rearrangements, we look at the paradoxes, we look at the derivations. So that's where I think even the particle accelerations, when you consider relativistic effects, it's very easy to get tripped up on the first question and then you just stumble your way through the section 2, 15 marks. And some kids just don't answer whole comprehension sections as well. So it's different. You have a strength in a certain area. that Robert won't, and vice versa. You might like projectile motion and be crap at circular. All right, that's the whole thing about this year, guys. You identify where you are lacking and you strengthen it, because the tests are low weighting, and it's the exam that's going to determine your ATAR. So you've got to say, right, I bombed out in circular motion. I'm going to beef up my circular motion because it's going to appear in the end of year exam and the WACE exam. Okay. So identify your weaknesses and work on strengthening them. Now, I had this Hubble comprehension question sitting in my Year 12 folder, and I'll give it to you. I don't know where the solutions are. It may have come from like an old exam, but I just thought, I could have really attached this to our cosmology booklet. It's a fun graphing exercise with some gradients and some calculations, so this will keep you busy. I will attempt to find. Hang on. I will attempt to find the solutions, and maybe when you guys come back next term, I'll have them up on hang on. Okay. You can prove it.